divide by spacing. Okay, so we know that V, okay, so V over here is 35 times 10 to the power 3, 772 times 10 to the power minus 6, divided by I. So I, you can see, is given down there, 0.270236 times 10 to the power minus 3, equal to force resistance. And we have to multiply by 2. This is because double shear. And then you divide by spacing of 0.25. So force resistance is equal to 35 times 10 to the power 3 multiplied by 772 times 10 to the power minus 6 multiplied by 0.25 divided by 2 divided by 0.270236 times 10 to the power minus 3. Okay, so this will be equal to 35 772 minus 6 times by 25 divided by 2 divided by 270,236 power minus 3 is equal to 12.498 times 10 to the power 3 Newton. Okay, so I say this is a bit confusing. Okay, you have to apply this rule. Okay, once you apply this rule, member must entirely distribute the shear stress. Okay, then you'll be fine. And without this rule, you say, Eugene, you mentioned that it cannot cross the first moment of area, and the centroid, the first moment of area cannot cross the centroid, but you did. Okay, so why is it? How is this possible, right? So this is why. We're gonna do another. Not difficult. I think in terms of confusing, this is pretty confusing. Let's do another one. Okay. Yeah, you can see this, we're like, whoa. Right? If you look at it, it can be scary, but it's not scary. It's the first moment of area that you have to look at. Okay. So again, I'm not going to calculate. So this is the value that I'm going to tell you all why it is like this. Okay. What area are we considering, right? So if you look at this structure now, right? So the member, so this is our Vy, okay? And you can take this as a thin wall. Let's combine thin wall analysis with this. Okay, let's combine thin wall analysis with this. So we know that the shear flow, right? The shear flow has to do this, right? Right. Then once it occupies the whole T section, then it will transmit the load on the bolt, right? So the first moment of area to take is the entire T section. You only need to consider the top half. You don't need to consider the bottom half because the first moment of area you only need to do at the top half. Okay. So for this case, so we are going to calculate the Q. Okay, the Q. So I'm going to calculate the Q of the flange plus by the Q of the web. Okay. So the Q of the flange is 3 inch. The depth is 0.5, right? So if you look at the Y bar, so 1 plus 3, so 4.5, right? So this is 4.5 minus by 0.5 divided by 2, okay? Plus, okay? So plus by, wait, I might have got it wrong. No, yeah, it's correct. Okay, plus the width is the width now is what, 3? Wait, let me see. I might have got something wrong. No, it's correct. The width is 0.5. The depth now is 3. The y bar is 4 minus by 3 divided by 2. Okay. Let me check again. The width is 3. The depth is 0.5. 3, 4, 4.5, 0.5 divided by 2, correct? The width is 0.5, the depth is 3. 3 plus 1, 4, 3 divided by 2. Yep. So 4.5 minus 0.5 divided by 2. 4.5 minus 0.5 divided by 2. That's 0.5 times 3. So it's 6.375 plus 4 minus 3 divided by 2. That's 375.5 is 3.75. I'll do it again. 3 times 4.5 minus 0.5 divided by 2. That's 0.5 times 3. 6.375. 0.5 times 4 minus 3 divided by 2. That's why 3 times 3.75 plus by 6.375 is equal to 10.125 inches cubed. Okay, so if you look at the answer, it's the same as 10.125. Okay, let's look at another very bad one. Okay, when I say very bad, a lot of times students struggle with this. Okay, if I can find it, I will show it to you. I mean, it's not confusing. Okay, this one. Okay, you will not have this. Okay. Okay. So this one is this one is I'm glad that I've taught all of you how to do thin wall first. Okay, before we come this problem. So this problem, where it's going to fail, we know that it's going to fail here, and it's going to fail here, right? So if you look at this problem, right, you will say, hey, how is this going to fail, right? This is pretty confusing. So I'm going to sketch this out. And we'll sketch this out. So you have two of these. Okay. Okay. And then you have one horizontal web. Come on, Eugene. You have one horizontal web over here. And then you have one vertical web over here. Right. And then we have faster. So we have three different fasteners. 1, 2, 3. Right. So we're going to design the shear flow first. Okay. Remember, major web control the flow. Right. This one will come in. This one will do this. Okay. So now on the nail, which is the horizontal nail. So let's call this horizontal nail. Okay. H1. And this one is H2. Right. So we know that failure will occur here. Right. We know failure will occur here. Failure will occur here. And failure will occur here. Right. So to find H1, or the failure at near 1, we only need to consider this force over here, or this first moment of area. Why? Because the left nail and the right nail are what? Independent. So you only need to take one area. Okay. Then the next one, okay, which is a bit confusing, is we have our vertical nail here. So for the vertical nail, the first moment of area you have to take is this entire area over here. Okay, because all the shear flow is going to come into the what? Into this region over here. Okay, so that is how you solve a problem like this. Okay, so what I'm going to do is I'm going to stop now. Okay, this is the last lecture on shearing stress. We are not going to do any more. Okay, I will see you on week 11, and week 11 we're going to start with mole circle. Okay, if that's the case, those that need to write the correction, I will see you on Thursday. Again, Thursday no lecture. Okay, good night.